Hi, this is our second video on depth-first search. Here we're going to present our final draft of depth-first search that does not use recursion and does not have the potential stack overflow issue in programming languages like C++ without tail recursion. So there's going to be two variables that keep track of the state of the search. I want to introduce those before we look at the pseudocode. One is a vector called scene. This is kind of a parallel array or parallel vector. It's a vector of booleans that track whether every vertex has been visited or not. So in our recursive pseudocode, we had this notion of keeping track of whether a vertex was seen or not. Every vertex starts out unseen, and then we mark it seen. So to implement that more concretely, we're going to create a vector of booleans, and the invariant is it's n long. So for every vertex index v, seen of v is true if and only if vertex index v has been visited already. So if we've done the visiting of v, then seen of v needs to be true. If we have not done the visiting of v, then seen of v is false. So that's one of the two state variables. The other state variable is called to-do. This is the new thing. To-do is a stack of vertex indices that need to be considered. That information was stored implicitly by the recursive process in our recursive algorithm. Now we need to explicitly keep track of that information in a stack data structure. In a sense, this is kind of an inbox of vertices to process. So the way that the traversal will work is to begin with the start vertex goes in this inbox, and every time we find new vertices that need to be dealt with, we add them to the stack. So we add them to the inbox. It's like a work inbox, like an email inbox or an old-fashioned paper inbox. As new incoming work comes in, it gets thrown in the stack, and then we deal with it when we can. So here's the invariant on the to-do stack. Vertex v is in to-do if the traversal can reach v. So if the traversal process has the potential of reaching vertex v, and we know that, then v is in the stack. If the traversal process can't reach v, or we've already dealt with it, then v is not in the stack. A corollary to these definitions is that if vertex v is in the to-do stack, then seen of v could be true or it could be false. So note that I didn't say it's a stack of vertices that need to be visited. Sometimes a vertex that's already been visited can go in that stack a second time. So some of the vertices in the stack are visited, some aren't. To be sure about whether we should traverse into a vertex, visit it, we need to check this seen of v flag. So here's the algorithm based on those definitions. Again, here are these invariants. So seen of v is true if and only if vertex index v has been visited already. And vertex v is in the to-do stack if the traversal can reach v. So all of the vertices that we know we can reach need to go into the stack. So here's my algorithm. At depth first search is given a graph G and a start vertex to start from. Here I'm creating my vector of booleans called seen, and I'm using the initialization method where I say the number of elements of the vector. This is the fill constructor, and I want to fill them all with false. So g.vertex count, that's n in the math notation, that's the number of vertices in the graph. So seen is a vector of booleans of the appropriate type. They're all initialized to false. That's marking every vertex as not seen according to this invariant. I create my stack of ints called to-do. I'm using int because that's the vertex index data type that we're using. So to-do is this stack that keeps track of vertices that we can reach. And to begin with, we only know about one such vertex, which is the start. So we push the start vertex onto the to-do stack. Now we go into the loop that does the traversal. So as long as the to-do stack is not empty, we keep going. So as long as there's vertices in the inbox, we deal with one and move on. So the next vertex to deal with is the top of the stack, and then we pop that element off the stack. And that decreases the size of the stack. That's why this eventually will become empty and the loop will terminate eventually. Now, we don't know whether this next vertex has been seen or not. Again, this invariant says sometimes a vertex on the stack has been seen, sometimes it has not been seen. And the goal is to only enter vertices that have not been seen to prevent an infinite loop. So if not seen of next, this exclamation point is the Boolean negation operator. So if not seen next, so if we haven't seen the next vertex already, we visit next, set its flag to true. That's to keep this invariant obeyed, that I've now visited next, so we need to set that flag to true to remember that from now on. And then we have this for loop for every vertex v in the out edges of next, push v onto the stack. So we're not doing recursion. That to-do.push v is the moment where we would have done recursion in the recursive algorithm. Instead, in this loop, I know that V is a vertex that our traversal can reach because we're at next, we're visiting next, and every vertex V that has an edge from next to V is reachable by the traversal. So every vertex that meets that criterion gets pushed into the to-do stack, and we'll look at it later. In a future iteration of this while loop, we'll consider whether or not we need to actually visit that vertex or not. Okay, so now let's run this to get a feeling for how it works. It's similar in spirit to the recursive version, but there are these state variables to keep track of, so it looks a little different to run. So this is the same pseudocode as the previous slide, and the first thing that happens is we create this scene vector. So I have that sketched here. So for every vertex index v, 0 through 4, so this is the graph G, it has vertex indices 0 through 4, we have a Boolean flag, scene of v, and I'm using the standard convention, 0 means false, 1 means true. So to begin with, they're all initialized false. We haven't seen anything yet. And then we create a stack called to-do, and I've sketched the stack here. It's empty to begin with, so there's nothing in it. And the first thing we do is push the start vertex onto the stack. So I'm starting at 3, so 3 gets pushed onto the stack. It goes in the inbox. That means we need to deal with 3. So next, the stack's not empty, so we repeat. And next is the first element of the stack. It's a little bit of a waste that we push 3 on there and pop it off again, but it makes the algorithm work and simple, so it's not a huge problem. So the next vertex to deal with is the top of the stack, which is 3. I've noted that here. And we pop next off the top of the stack. So now the stack is empty again. And I haven't seen 3. 3's flag is false here. So we visit 3. I'm going to keep track of the order that we visit the vertices. So 3 goes down in the list. We set 3's scene flag to true because we just saw 3. So set that flag to true. That'll prevent an infinite loop going into 3. And now we have this loop. For every out edge of 3, we push that vertex onto the stack. So the first out edge of 3 is 1. The second out edge of 3 is 4. 1 and then 4 get pushed onto the stack. So now we're done with vertex 3, and the loop will repeat. Now, the to-do has 2 elements. It's not empty. So we repeat again. The next element is going to be 4, the top of the stack. We pop 4, taken off the stack right there, and check, has 4 been seen according to my vector? And the answer is no, we have not seen 4 yet, which is correct. So we visit 4. So I'm adding 4 to my visited list, and set 4's scene flag to true. And then we loop through all of 4's out edges, and there's one of them, 0. So we push 0 onto the stack, and then repeat again. So I'm going to speed up a little bit at this point because the pattern is starting to become clear. So we pop 0 off the stack. 0 is now the next vertex. We add 0 to the list and set its scene flag to true. And then for every outgoing edge of 0, we push onto the stack. So 1 is an outgoing edge of 0, so we push it onto the stack. Now notice, 1 is on the stack twice, and that's what I said. This can happen. So 1 was recognized to be reachable by 3. So early in this process, we saw that 3 has an edge to 1, so we pushed 1 onto the stack. Then we did our depth first search thing where we sort of ran down this rabbit hole. We flew as far away from 3 as we could, and we ended up wrapping around and hitting 1 again from a different side. And that can happen. So 1 is on there twice. It's going to work out to be okay, but that can happen. Okay, so now we repeat the loop again. 1 is going to be the next vertex. So we pop the first 1 off the stack, and 1 has not been seen yet. So we visit 1, add it to the list, set 1's scene flag to true, and then for every outgoing edge of 1, push onto the stack. There's one outgoing edge, which is the 2, so 2 gets pushed onto the stack. So now we go around again. Again, we're going to go a little faster. 2 gets popped off the stack. 2 is next. We visit next, which is 2, put it on my list. And then for every outgoing edge of 2, push onto the stack. So we push 3 onto the stack. Again, note that we already visited 3. 3 ended up on the stack a second time. It's okay. It's not going to hurt anything. Okay, so we can, again, human-wise, visually see that we're done traversing everything. We visited all 5 vertices in a particular order, but the algorithm hasn't quite caught up yet. It'll just wrap stuff up. So what happens next is the stack is not empty, so we pop the top, which is 3. However, we have seen next. 3's scene flag is true, so this inner loop does not repeat. We don't visit 3 a second time. We don't look at its neighbors, we just pop 3 and move on. And then the same thing happens the next time. The next is 1 that was in the stack. We pop the 1 out, and 1 is already seen, so we don't reprocess 1. We're done. And now the loop is done because now the stack is empty, so we finish.